Assalamu class. Welcome back, and let's continue the chapter number 11. And in this lecture we will consider HDLC and its modes, its frames of communication, and at the end we will consider authentication protocols. So first, something important about HDLC. So HDLC was developed by ISO, International Standard Organization, and it offers levels of flexibility, adaptability, reliability, and efficiency of operation for synchronous data communication needs. Its features are: HDLC is a bit-oriented data link control protocol supporting point-to-point and multi-point communications, two-way simultaneous or alternate communication over full duplex circuits, communication between equal stations, and between host and remote stations. And it shows full transparency of data. That means everything in the frame is very much transparent, and it can be understood with respect to the syntax and semantics of the frame. The ISO standard for HDLCs are ISO 3309, 4335, 6159, and 6256. So HDLC implements the ARQ mechanism, which we will discuss later in this chapter. So first, let's try to understand what type of stations our HDLC has. So in a network, when we are using HDLC, there are three types of stations that are defined, which are primary, secondary, and combined stations. What is a primary station? A primary station has the responsibility of data link management, that is activation, maintaining, disconnecting of data link. So he is the basically boss of the network. A secondary station operates under the control of a primary station. The primary station sends commands, frames to a secondary stations which are working under it, and the secondary stations then can send frames called responses. A combined type of station can act both as a primary and secondary station. Communication can be between two logical equal status computers, also in which the case they are designated as combined station and can receive both commands and response frames. So in this case, both the stations which can handle the commands and responses, they are called combined stations. So to communicate in a network, we see that there is a two type of modes, which are normal response mode (NRM) and asynchronous balance mode (ABM), which we will discuss in detail later. So this diagram shows you a picture where you can see a point-to-point communication, a multi-point communication, and at the end you can see a communication between the two combined stations, which is based on full duplex. So the first setting of the network, these two, they are called normal response mode, and this one is called asynchronous balance mode. We will discuss this later in next slide. So the stations are generally in disconnected mode. The primary station send mode setting command frame to activate them and to bring them under a certain data transfer mode. So basically primary station is responsible for all the mode conversions. There are three types of modes. Two are basically the modes which we have discussed previously, but the last one, which is called initialization mode, we will discuss what is initialization mode later. First, let's talk about the normal disconnection mode. The normal disconnection mode stations usually are in this mode when they turn on in a network. Asynchronous disconnected mode, a system can move into asynchronous response mode and a balance mode, which we've discussed earlier in the previous slide. So what is initialization mode? IM. It is used to set exchange parameters. If you want to exchange the parameters, you want to change them, you can move into initialization mode, and from here you can move into any of the mode which is ARM or ABM. Station move in this mode when it finds an abnormal functioning of a secondary station, or itself requests to move in this type of mode when it needs to move into any of the modes. Later, let's talk about the transition modes. We can understand these modes better using mode transition diagram. Asynchronous disconnected mode, a normal mode which a system when turned on will find itself at start, and similarly other modes can be reached from here onwards. So here and here we can move. which is ABM or ARM. And similarly, initialization mode, which is considered ideal, can also be reached. This is initialization mode. As discussed previously, a station may have a normal disconnected mode, where stations activate into normal response mode is shown in the diagram here. Similarly, if a station finds that it cannot do a proper communication, then from NDM, the station moves into IM, which is in the middle part, initialization mode, and from there it can move to normal response mode, NRM, which is here. If it cannot move from here, there is a problem with the communication here. Similarly, ADM is a disconnected mode. A station can move to ABN and ARM, and based on the conditions, the abbreviation mode settings are defined below. So the S in the middle is a diagram shows the setting of different modes and their transition to other modes, and their forms are given below too. So let's move on and let's talk about HDLC flow and frames. First, HDLC flow control. HDLC utilizes sliding window flow control mechanism, and the window size can be either 7 to 127. Error control is based on retransmission of frames arrived with errors. Error detection is carried out using 16-bit CRC. So let's talk about the HDLC frames. There are two types of frames that can be used by a sender in HDLC. The two types of frames, as you can see in the diagram, are called I frames and the U frames, whereas the sender can't send the S frame because S frame is the acknowledgement frame. All the fields have a fixed length except the information field, because the information field we are sending the data and the data is of variable length. Two frame delimiters are used. The frame is transmitting from left to right and the lower bit is transmitted first. So we got I frame, which is called information frame, then we have S frame, which is supervisory frame, and then we have U frame, which is a unnumbered frame. Each type of frame serves as an envelope for the transmission of different type of messages. I frames are used to data link user data and control information relating to user data, which is called piggybacking. S frames are used to support control information. U frames are reserved for the system management. Information carried by the U frame is intended for the managing link itself. Each frame in HDLC may contain up to 6 fields as shown in the figure. A beginning field flag, an address field, a control field, an information field, a frame check sequence field, and a ending flag field. In multiple frame transmission, the ending flag of one frame can serve as the beginning flag of the next frame. Let us now discuss the fields and their use in different type of frames. Flag field, the first one here. This field contains synchronization pattern, which is 0, then followed by 6 ones and then 0, which identifies both the beginning and end of the frame. So they both are the same as explained in previous lecture. Next is the address field. An address field contains the address of the secondary station. If a secondary station creates a frame, it creates a from address. The address field can be 1 byte to several bytes long depending on the need of the network. Next is the control field. A control field is 1 or 2 bytes used for flow and error control. The interpretation of bits are discussed later. Next is information field. The information field contains the user data from the network layer or management information. Its length can vary from one network to another. Frame check sequence field, FCS, is the HDLC error detection field. It can contain either 2 or 4 byte CRC. The common field determines the type of frame and defines its functionality. So let us discuss the format of the field in detail. The format is specified for the type of frame as shown in the figure. So here onwards we will discuss the control fields of the I frame. We will discuss about the S frame control field and we will talk about the U frame control field. So let's first talk about the control field for the I frames. So in a two-way communication, let's see how the frames are sent and received in a piggyback scenario. So the iframes are designed to carry user data from the network layer. In addition, they can include flow and error control information, which is called piggybacking. The subfield in the control field are used to define these functions, and these functions are as following. The first bit defines the type. So here we can see the first bit that defines the type of the frame. The next 3 bits called NS defines the sequence number of the frame. So the 3 bits then define the sequence number of the frame. Note that with 3 bits we can define the sequence number between 0 and 7. The last 3 bits called NR correspond to acknowledgement number when piggybacking is used. The single bit between NS and NR is called a PNF bit. So this is PNF bit here. The P or F field is a single bit with a dual purpose. It has meaning when it is set to 1 and can mean pole or final. It means pole when the frame is sent by a primary station to secondary, when the address field contains the address of the receiver. It means final when the frame is sent by a secondary to a primary, when the address field contains the address of the sender. So let's move on to the control field for S frame. Supervisory frames are used for flow and error control whenever piggybacking is either impossible or inappropriate. S frames do not have information field. If the first 2 bits of the control field are 1, 0, this means that the frame is an S frame. The last 3 bits called NR respond to the acknowledgement number ACK or negative acknowledgement number NAK. Depending on the type of S frame, the 2-bit called code are used to define the type of S frame itself. With 2 bits, we can have 4 types of S frames as described below. Receiver ready. If the value of the code subfield is 00, it is an RR S frame, means receiver ready. This kind of frame acknowledges the receipt of a safe and sound frame or group of frames. In this case, the value of NR field defines the acknowledgement number. Receiver not ready. If the value of the code subfield is 10, it is an RNR, which is receiver not ready sub S frame. This kind of frame is an RR frame with additional functions. It acknowledges the receipt of a frame or group of frames, and it announces that the receiver is busy and cannot receive more frames. It acts as a kind of cognition control mechanism by asking the sender to slow down. The value of NR is the acknowledgement number. Reject REJ is the value of the code subfield is 01. It is an reject S frame. This is a negative acknowledgement frame NAK, but not like the one used for selective repeat ARQ. It is a negative acknowledgement that can be used in go back N ARQ to improve the efficiency of the process by informing the sender before the sender timer expires that the last frame is lost or damaged. The value of the NR is the negative acknowledgement number. Selective reject SREJ. If the value of the code subfield is 11, it is an selective reject S frame. This is a negative acknowledgement frame used in selective repeat ARQ. Note that the HDLC protocol uses the term selective reject instead of selective repeat. The value of NR is that negative acknowledgement number. So let's move on and let's check out the U frame. Unnumbered frames are called U frames, are used to exchange session management and control information between connected devices. Unlike S frame, U frame contains an information field, but one used for system management information, not for user data. As with S frame, however, much of the information carried by the U frame is contained in code included in the control field. The U frame codes are divided into 2 sections: a 2-bit prefix before the P or F bit and a 3-bit prefix after the P or F bit. Together, these 2 segments, 5 bits, can be used to create up to 32 different types of U frames. So let's talk about example number 1, where we will be discussing connection and disconnection. The figure shows a U frame can be used for connection establishment and connection release. Node A asks for connection with the set synchronous balance mode SABM. Node B gives a positive response with an unnumbered acknowledgement UA. After these 2 exchanges, data can be transferred between the 2 nodes as shown in the figure. Data transfer is here. After data transfer, node A sends a disconnect frame to release the connection. It is confirmed by node B responding with a UA, unnumbered acknowledgement. So in the next 2 figures, we will see exchange of data using a piggyback. The first is the case where no error has occurred, and in the second one where an error has occurred where some frames are discarded. So let's move on and let's talk about a little bit about authentication protocols. So authentication plays a very important role in protocols because protocols are designed for use over dial-up links where verification of user identity is very important. Authentication means validating the identity of a user who needs to access a set of resources. Protocols have been created, and these protocols are of two different types for authentication. One is called password authentication protocol, and the second one is called challenge handshake authentication protocol. Note that these protocols are used during the authentication phases. So let's talk about password authentication protocol. It is the simplest authentication procedure with two steps process. The user who wants to access a system sends an authentication identification, usually the username and a password. Number two, the system checks the validity of the identification and password and either accepts or denies the connection. The figure shows a three type of packets used by PAP, which is called PAP, and now they are actually exchanged. When a PAP frame is carrying a PAP packet, the value of the protocol field is 0xC023. The three packet authentication protocol packets are authenticate request, authenticate acknowledgement, and authenticate negative acknowledgement. The first packet is used by the user to send the username and password. The second is used by the system to allow access, and the third is used by the system to deny the access. So let's move on and check out the second authentication protocol, which is called CHAP, Challenge Handshake Authentication Protocol. Is a three-way handshaking authentication protocol that provides greater security than password authentication protocol. In this method, the password is kept secret. It is never sent online. The system sends the user a challenge packet containing a challenge value, usually a few bytes. The user applies a predefined function that takes the challenge value and user's own password and creates a result. The user sends the result in a response packet to the system. The system does the same. It applies the same function to the password of the user, which is known to the system, and the challenge value to create a result. If result created is the same as the result sent in the response packet, access is granted. Otherwise, it is denied. CHAP is more secure than password authentication protocol, especially if the system continuously changes the challenge value. Even if the intruder learns the challenge value and the result, the password is still secret. Figure shows the packets and how they are used. CHAP packets are encapsulated in the protocol frames with the protocol value C223 in hexadecimal. There are four CHAP packets: challenge, response, success, and failure. The first packet is used by the system to send the challenge value. The second is used by the user to return the result of the calculation. The third is used by the system to allow access to the system. And the fourth one is used by the system to deny access to the system. So that concludes the lecture. Thank you very much for watching. Till next time, take care. Allah Hafiz. In next lecture, that is chapter number 12, we'll come back and we'll talk about media access control and protocols associated with it.